So again, we're going to be talking about Faraday's law and Lenz's law. The truth is, Lenz's law is an application of conservation of energy, and it amounts to a minus sign in an equation. But yesterday we talked about what Faraday's law looks like, and it doesn't look particularly complicated until you begin to understand all the parts of it. It's on. I just may not be connected to it. Maybe it's off. I don't know. Thought I did hit the button. It's on. It's not warmed up yet. I guess we wait a minute. There you go. All right. So, two things. First, this little negative sign is Lenz's law. So you're going to say, why isn't the answer negative? I'm going to tell you right now, the negative sign is a part of the law, but it is a reminder for you to try and figure out the direction of the EMF or any induced current. The negative itself is immaterial in the law. I'm presenting the law as it is on your equation sheet, but I want you to be aware that your answer is not positive or negative. We look at using of Faraday's law as getting the magnitude of the EMF, but the negative sign reminds you that you have to use Lenz's law to figure out the direction. Everybody understand? So that's why the negative is there. So in 20 minutes, when the first one of you asks me, why is it not negative? I get to slap you. Do we understand? Okay. Oliver, did you hear me? Okay. Oh, I do remember that. You had your big moment, and not so much. All right, so let's look at the pieces real quick. And I'll level with you. I like talking math. I like the symbology of math. I like that it communicates things elegantly and efficiently. And I've kind of played it that way the entire year. I've developed an understanding about the people in this room. And some of them are okay with it, and some of them look at that and are just like, oh, I don't care what the hell it is. That means nothing to me. So look, to all of you, stop being like that. This is communicating something to you, and you should be smart enough to understand what it is. You're grossly trying not to understand it if you can't see the pieces that are there. Because every piece there is something that has been talked about. And pretty thoroughly. The only thing here that might be a surprise or you might not know what it is that. And that one's pretty straightforward. Number of loops. Faraday's law requires a closed loop, at least one. Because it has to be a complete circuit or else there can't be a current. This is not talking about motional EMF like we talked about the other day. This is Faraday's law. So Faraday's law begins with some kind of closed conducting loop. There's a derivative there, a derivative with respect to time. So understand that nothing happens unless something changes over time. That's what all of this is telling you. That if the thing is constant, there will be no EMF. There has to be some part of it that changes over time. Now, I'm not seeing enough pencils wiggle there for the people who have questions always. So, by changing over time, be careful. Not changing over distance, not changing over place. Something has to happen with respect to time for there to be an EMF produced. I'm saying that because flux has to do with space, and it's going to have an integral in it. So we're taking the derivative of the result of an integral. You already know the definition of flux. This is magnetic flux, not electric flux, and the integral is just B dot dA. Notice no circle on the integral. We're talking about having a loop of wire, and in this case, the area represents the area of that loop. But it's a sum of the magnetic flux through that loop. That's why it's a summation. That's why it's an integral. So you have to first find out the amount of flux through your loop and then look and see if that flux is changing. If that flux is changing, then you're producing an EMF. Everybody follow along with all that? Those are all the pieces. I've tried to break down the pieces as clearly as possible. You could write Faraday's law like this. If that makes you feel better. But for some people, and for me included, that's not better. It's more cumbersome. So I've been very clear about what each piece is. We good? Now, I want to also indicate this. The order in which you should use Faraday's law is this order. You should calculate the flux first. I'm not going to write down this list of steps. I already taught chemistry today. So you should calculate the flux first. That may or may not be something that's relatively straightforward. Usually it is. You've seen the kind of flux calculations we're going to have. There'll be a few others, but you've seen most of them. Then you should look at it closely and see if any part of it is changing with respect to time. That can be the harder thing to deal with, because you're going to have to take the derivative with respect to time. Once that's done, multiply by the number of loops, your easiest step. But don't forget it, because you look like a fool if you do. And then deal with the direction. It's going to be completely separate. It's going to be a right-hand rule thing. Now we're gonna do a problem that you've already done. And that's what's going to be great about it. It should be easy. And we're going to apply Faraday's law to it. We're going to do the motional EMF problem that we did yesterday. But we're going to do it using the way Faraday's law is constructed, as opposed to looking at the forces on individual charged particles. So let me do that for you. That's going to begin with a loop. And I'm going to use a rectangular loop because it's easier. Oops, that's not a rectangular loop. Mr. Shelton needs to learn his shapes. There's a rectangular loop. So this is our rectangular conducting loop. I'm going to have a region of space that is filled with a uniform magnetic field. A phrase you're going to hear quite a bit. And I'm going to give the whole loop some velocity v. All right. Let's add some dimension to this, just so we have some dimension. This we'll call L, and this, let's not do it that. Let's try and be consistent with yesterday. We'll call this W, and we'll call this L. All right? Now, right now there is no flux, right? There's no magnetic field, inside the loop, so there is no flux. But I'm kind of imagining a moment, in the future where we breach the magnetic field, and now we have a small amount of the magnetic field is inside my my loop. Now, here's where, when you take a look at Faraday's law, you have to kind of figure out what is the part of this that is changing with respect to time, so that you can begin to establish how you're going to calculate your EMF. First, to calculate flux here, I need to have a region of space inside my loop that is filled with a magnetic field. And I do. I have this small section right here where there is a magnetic flux. I don't currently have a value to represent how much of the area is filled with magnetic field. So this is one of those moments where you might have to create a temporary variable to help you in your calculation. Now, if you don't see where I'm going with this, look, yesterday we proved that this has something to do with the velocity of the loop. But area has to do with how much of the loop is currently inside the magnetic field. I see a future where this length is probably changing. Do you see a future where that length is probably changing? In fact, I think it's probably related to this variable. In fact, in my opinion, it might be appropriate for me to think of a future where I understand that something is changing with respect to time, and I have a relationship already in mind that I might be able to use. So for all of you people who don't remember mechanics or did not have the calculus version of mechanics, something's velocity is the rate of change of its position. So knowing I'm likely to need velocity later, I'm going to tuck away and I'm going to say that this is length x. So there we go, length x. That's how much of my loop is inside the magnetic field. Because step one is have a means of calculating flux. So there's step one. I'm going to try and calculate the flux. Flux, remember, 3 parts. Magnetic field, something to represent the portion of the area, and the angle between the magnetic field and the direction of the area. All right, so reminder that all 3 of those things have to be considered. Let's start with the dot product first. Can we kind of agree that we're looking at a cosine of 0 degrees? All right, I have a area that is directed into the board and a magnetic field directed into the board. So first thing I'm going to do is strip away the stuff that has to do with that. No dot product now. We've lined them up. It's cosine of 0. Next thing I'm going to realize is that it's a uniform magnetic field, and everywhere inside my square has the same magnetic field. That suggests that my next step is to go ahead and pull the magnetic field out front. It's constant. Now I'm going to go ahead and construct my area. And I see my area as being pretty easy to construct. I think we can write that as x times L. Right, the magnetic field is a constant, so I'm just summing the whole area. And the whole area is the area that's filled in green, x times L. We good with that? Pretty straightforward? All right, we have done step 1. We have successfully calculated the flux. Moving on to step 2. Step 2 requires that we take the time derivative of the flux. So now I'll move to step 2. Let's do that right here. This was step 1. So step 2. Take the time rate derivative of the flux. Well, do any of those variables change with respect to time? Yes. Is the magnetic field changing with respect to time? No, it's constant. I can pull it out. Is x changing with respect to time? Yes. Yeah, we already established that. That amount of area is getting bigger because x is getting bigger. So the first thing I would do is recognize that x is changing with respect to time. Tuck that away. Is L changing with respect to time? No. So the very first thing I would probably consider doing is pull out the things that aren't changing, and then what you're left with are the things that are changing. Time rate derivative of the flux. And we already know what this is going to be. This is going to be BL times V. That's how fast it's going. The derivative of x with respect to t is the velocity of the loop. Now, as of yesterday, we talked about it being a single loop because we only had one loop yesterday. This was a single loop, so the value for n here is 1. And as I said before, don't leave the negative sign in there. The negative sign is a reminder that you have to use Lenz's law. So when asked what the EMF is for this situation, I think we can effectively say it's exactly what we figured out yesterday, BLV. Where we used Faraday's law to come up with it and not and not emotional EMF, and dealt with forces on charged particles and such. We already have a method for determining the direction of this current too, don't we? And you should be able to do that. Right-hand rule based on the motion of the force in the charged particles. That's not how I want you to do Lenz's law. It works here, but it's not how I want you to do Lenz's law. I want you to use something else. But since that's all you currently know, can you direct the current? Is it clockwise or counterclockwise? Use your right-hand rule, magnetic field. Remember a positive charged particle. So I'm thinking positive charged particle is going to be pushed up. When I saw all of you people pointing towards the door, I felt happy. Except for your people pointing with your left hands. 2 of you checked, but you both had your right hands out. That was nice. That gave me happy thoughts.
The cross mean is out of the board? Like the X cross?
Into the board.
Oh, yeah.
So current this way, right? If I was to try and draw a picture of the EMF, I could draw a battery like that, and that would produce the same thing. But remember, the EMF is a voltage. The result of calculating this gives you a value in volts. It is an EMF. However, it's an EMF that doesn't have a potential difference source. So there's no battery in the circuit. There's no place where you would place the battery here. This is happening right now just for the parts of the wire that are entering the magnetic field, but we're going to have a situation in a minute where that's not true. So we do okay with this? Pretty straightforward? Okay, so we're going to see another example. Ready for the next example? That works here too. Before we put the loop into the magnetic field, is there any flux? So as we try and push this loop into the magnetic field, the current created is going to try and oppose this change in flux. So there was no magnetic field before. Now I'm suddenly pushing a magnetic field into this loop that is into the board. The current has to create a magnetic field out of the board. It creates a magnetic field that is in opposition to the change in flux. So it works here too. You all right with that? Same loop. Region of space with a magnetic field into the board. Uniform magnetic field. The magnetic field is given by AT plus B, where A and B are positive and non-zero. What does that tell you about this? What can you tell me about the magnetic field? It's increasing. It's getting bigger. Everybody follow along?
Yes.
So this is a different situation. I have a magnetic field that has a clear time rate of change. Okay? I'm not going to move the loop. So we're still going to have the same size constraints. So I have this side is L. This side is W. It's a single loop. The magnetic field is changing with respect to time. Now, step 1, calculate the flux. Evaluate the cross product. Are we good with cosine equals 0? Is that good for you guys? All right. Is the magnetic field a constant everywhere in the loop?
Yes.
Yes.
Now, I want to be careful about the way we phrase our questioning now. I'm not saying that the magnetic field is constant, but I'm saying that it's the same size everywhere in the loop. This tells us whether we have to integrate across the area or not. So the magnetic field doesn't have to be the same size over time, but is it the same value everywhere in the loop? So those are questions that I'm trying to be careful about the wording of. And I would encourage you to, if this is something where you would get confused, to give yourself a reminder. You're asking if the magnetic field is the same across the area during step 1. You're not asking if the magnetic field is the same all the time. There's a difference. And this is why I'm trying to be very diplomatic about it. I'm also trying to be patient while I watch people who don't normally take great notes take the best notes they've ever taken. All right, I'm trying. I can pull the magnetic field out then if it's the same everywhere across the area, and now I just need to sum up the area. And in this case, that'll be length times width. So this is my flux. Now, it is plausible, if you were asked to do this on an AP exam, that you would not be able to submit that for your flux, and you would have to submit that as your answer for flux, if they say B can't be in your answer. Some of you have always come up to me and said, well, what if I left B in there and didn't put AT plus B instead? You know what the answer to that is, right? You get it wrong. You don't get the point.
On an FRQ question, if they ask us to derive, those are the steps that we would show.
That's why I'm going through it. Yep. All right, step 2. Pretty straightforward. Faraday's law. The next thing we're going to do is take the time rate of, the time differential of my flux. Now, again, I think we can all pretty well agree without any trouble that that's the only part they have to worry about when it comes to the derivative. L and W are a constant, so they'll skip the derivative. They're going to be the same the whole time I'm taking the derivative. We good? You following me on that? So, when I take this derivative, minus N LW, I'm taking the derivative with respect to time of AT plus B. And having done this before, and so have you, the derivative can be distributed, and the derivative of AT with respect to T is just A, and the derivative of B is 0, because it's a constant. So this, after step 2, negative N LWA. How many loops is this? And do I include the negative sign in my answer?
No.
Don't need to, no. The magnitude of the EMF, LWA. Direction of the current. This is step 4. That negative sign is telling you to stop and deal with the direction of the current. Here's where we're going to need a little bit of an understanding. This won't be obvious now, and it's going to take a little time for you to develop. But Lenz's law, although is actually an extension of conservation of energy, Lenz's law actually acts like inertia. If you want to interpret Lenz's law correctly, the best way to do so is to understand this one sentence. You ready? It's complicated. There might be a semicolon in there. The direction of the induced EMF. The direction of the induced EMF is to produce a current that produces a magnetic field to produce a current that produces a magnetic field that opposes the change in flux. There's a lot of commas in that. Lenz's law. So, the EMF produces a current that produces a magnetic field that opposes the change in flux. I want you to think about this. There's no cues as to how you would use the right-hand rule to figure out the direction of this current. Right? With the motional EMF, you could figure out the force in a charged particle, but we don't have that this time, do we? The magnetic field is just changing. It's becoming a bigger magnetic field into the board. So how do we figure out the direction of this current? The direction of the current is to try and oppose the change in flux. Now, reason this out in your head a little bit. The magnetic field is getting bigger into the board. In order to oppose the change in flux, the current produced wants to maintain the magnetic field that's there. So the created current is going to create a magnetic field that's in the opposite direction of the change, which means the current has to produce a magnetic field out of the board. That's going to be a magnetic field that's in opposition to the change in flux. So if I make this magnetic field bigger, then the current produced is going to have to be in this direction to oppose the change in flux. Now, this is worth practicing once or twice just to see, okay? So let's practice once or twice just to see. Because I get you all nodding your heads and all, but let's try this one. I have a magnetic field out of the board. And I have a loop of current in it. The magnetic field is 5 Tesla. The radius of the loop is 10 centimeters. I'm going to turn off the magnetic field. What EMF is produced if the magnetic field shuts off in 5 seconds? During those 5 seconds that the magnetic field is being shut off, what EMF is produced? And what direction would it be produced? I want an answer. There's a numerical answer to this in volts. Again, the magnetic field goes from 5 Tesla to 0 in 5 seconds. I have a loop inside this magnetic field of 10 centimeters. I'd like to know what the EMF produced is during those 5 seconds, and what direction is it? Yeah?
Does it change like constantly? Because
I'll revise my statement to say that it goes from 5 to 0 in 5 seconds. I'd like the average EMF produced over those 5 seconds. That clears me of having to say whether it's constant or not. But you have nothing to go on but make it constant, so. We don't get numbers in here very often. What?
So, just to clarify, is that big sentence you were telling us the reason they put that negative in Faradays as well?
Did you guys hear it? I earned a slap, didn't I?
Yes.
No,
I totally
I
did.
understand why it's there. I'm just saying, is that
I earned the slap.
baseball bat. Baseball bat. I got one in my trunk.
I already answered that question. That was the whole thing.
Oh, I thought you were just doing that for fun.
Oh, just for fun. It's going to be fun. It's going to be fun.
Oliver,
Wait,
this
Oliver,
is your
were you
fault.
Bringing out the hand of God.
Oh, God?
I was very clear from the beginning, right? Wow.
Did you think it was going to happen, even though you said it?
I was pretty sure.
Actually?
I understood.
Look, there's a
why.
pattern. It's not. I mean, look, we're not on day one of this, right?
Right.
I'm sure there should be a pi r squared in this answer,
Yes.
where r is probably 0.1. This is going to be a tiny little EMF. It's not going to be very much. Magnetic field's going from 5 to 0 in 5 seconds. I'm seeing a rate of change of magnetic field of what? -1. Careful of your negatives and your positive, though. It could get you in the slap territory. Slappatory. It's like purgatory. You never know when it's going to happen.
You die, you disappear, Mr. Shelton.
You just sit there in slappatory, just waiting. So, flux first. A little nervous about how long this is taking. B.dA looks to me like magnetic field and the area are aligned again, so I can shoot that as a cosine equals 0 kind of problem. And I also think the magnetic field is a constant everywhere inside that loop, leading me to just need to find the area of that loop, which looks to be pi r squared. Pretty sure I can use this for my flux. What's changing on the magnetic field? How's it changing? Well, the magnetic field goes from 5 to 0 in 5 seconds. I think I can come up with a pretty clear idea of what dB dt is going to be. The rate of change of the magnetic field. Right? That's the only thing that's changing. And I'm pretty sure that's going to be 0 minus 5 over 5. Or, if you prefer, -1 Tesla per second. Now,
I'm sorry. dB is 0 minus 5.
change in magnetic field over change in time.
5 seconds.
I mean,
Okay.
for this, because it's uniform, it could be delta B over delta T. That's fine.
It's because the field is all throughout the circle and everywhere else, so it's not changing.
It's 5 Tesla, and it goes from, all that area is 5 Tesla, and it goes from 5 Tesla to 0 in 5 seconds.
Okay.
Okay? So, that suggests now that if I do -n d flux dt, what I really have is negative times 1 times -1 times pi times 0.1 squared. Right? Any problem with any of that? So my actual EMF, that's going to be 0.0314 volts. Direction. That's big boy here, right? The direction. See if you got that part right. That's got to be the direction of the current. The magnetic field is disappearing. So the current has to be in the direction that will try and prevent the change in the magnetic field. So I get a magnetic field out of the board because it wants to preserve the flux that was there. It's trying to oppose the change. Good? All right. How about this one? I've got wire. It's vaguely circular, like so, in a region of space where there is a magnetic field into the board. I'm going to pull the wire so that the area of the wire shrinks down. Everybody understand? We're going to assume the radius of this circle changes uniformly from 0.1, let's go with just a 0.1 meters to 0 in 5 seconds. Magnetic field stays constant. I'll say it again. I'm going to have the radius of this circle decrease from 0.1 meters to 0 in 5 seconds. So I'm just shrinking the circle. Everybody follow along? With the idea? It's the same problem as before, except we're changing the area over the 5 seconds, and we're not changing the magnetic field. I want you to figure out what the direction of that current has to be. This one's tougher. This one's tougher.